Okay, good evening, everyone. Thank you, Hassan, for this opportunity to speak here. Before I dive into the content, I'll just quickly introduce myself. I've got about 15 years experience in enterprise systems, management information, BI, mostly in the for-profit education sector. So I don't have any experience in the construction industry, so hands up to that straight away. So this is going to be a more generic talk. I was based mostly out of London and also Singapore. And a few years ago, I took a career break to do a master's degree in business intelligence at Birmingham City University, which is just over the road from here. And that was a very modern take on BI. Had a significant component of data mining and machine learning content. And one thing led to another, and I'm now doing research towards a PhD, really in the topic area that I'm going to be discussing today. So I'll introduce machine learning and specifically the black box problem. When we do machine learning, we take historical data, or we call it training data, pass it into a machine learning algorithm of some kind, and the output from that algorithm is a model, a kind of summary of the data that lets us do prediction or automated decision making on new data that wasn't contained in the training set. And the state-of-the-art methods that we have give us very high predictive accuracy, but they're hardly interpretable. It's very difficult to explain how each individual decision is made. And that is maybe because of the way that data is represented inside the model, or maybe the model is very complex in its structure. It might have many layers running in, or many processes running in parallel. So one example is a neural network. Now we can all see that this is a handwritten digit number 8. But for the neural network to classify which digit this is, we have to provide a numeric value for every individual pixel of the image, and then those numeric values are transformed mathematically or computationally through many, many layers before coming out with the output that's a handwritten digit number 8. So it's obvious that we, as humans, can't unpack the complex calculation that's happening in here. Another example is decision forest. This is the type of model that I normally work with in my research. I'm guessing some people in the room have heard of a decision tree or used a decision tree. Decision trees are very interpretable types of models. They're just a hierarchical structure of usually binary rules, something that's true or false about your data. And they're very easy to interpret and understand. A decision forest is made up of tens or hundreds or even thousands of decision trees. On the left-hand side, an idea of a random forest, where all of the trees are generated from random start conditions, so they're all a bit different. And they work in parallel and give you a majority vote in terms of the automated decision that comes out of them. A boosting model, which is on the right, is built sequentially, and every time a new tree is added to the model, it tries to correct the errors of the previous iteration. So you can probably imagine from that just looking at a single tree from inside one of these models, isn't going to give you any understanding of how the whole model behaves. And trying to contemplate all the trees at once, obviously, again, is impossible for us to do. It's quite a difficult computational problem as well. I think it's always quite intuitive to just go into 2 dimensions when we talk about machine learning classification, just to get some intuition about what's happening. So we want to build a model that can separate this data into 2 different classes, the red class and the blue class. And I've got some data superimposed on each chart. This is the training data superimposed. It's the same data on each chart. And you can see it's not very nicely behaved. The clusters are a bit interleaved. On the left-hand side, we're using just a logistic regression to separate the 2 classes, and everything above the line is going to be predicted as being red. and everything below is blue. Now, this model is just a straight line. Logistic regression can only find a straight line, and that's obviously unsuitable for this data set. But it's a very interpretable model. It's just a simple mathematical equation that someone with maybe a maths GCSE can handle and can interpret. On the right-hand side, we've got the decision boundary generated by a random forest with 1,000 trees in it. And there's no way for me to describe this line in any mathematical or English natural language. But it perfectly describes the data that we've got. So there's always this trade-off between accuracy and interpretability when we're trying to choose which model we want to use. Do we want to be able to interact with the model and talk about what it's doing and how it's classifying the data, or are we happy to accept a very accurate model that we can't explain? So I wanted to talk a bit about the legal, moral, and ethical issues that is thrown up by the black box problem. Anyone who's I'm sure has noticed a number of news features and current affairs items that talk about AI is just increasing in frequency. There's more and more discussion, more and more public discourse, and so we hear a lot day to day about these concepts like big data, profiling, micro-targeting of advertising content, and even political messaging. I'm sure you'll realize your social media feeds are curated algorithmically, and some of you may realize as well that your search engine results are also curated the same way. So that means that you and I might see different search results for the same search terms, and that's all related to the things that you've interacted with or shown any interest in, your digital profile or your digital footprint. So this idea that algorithms are controlling all the stuff that we see and do in the digital space, that even the owners of those models or those algorithms can't really explain properly. The idea that that's happening generates a real lack of trust, a real trust deficit in the general public, and that's quite justifiable. And as with everything related to data, it's garbage in and garbage out, and it's best manifested in machine learning when you have inherent bias in your training data. One of the something that came up in the news quite recently was a system that was designed to do facial recognition from passport photos for the kind of biometric passport gates. And it was much worse at identifying black and ethnic minority faces than white faces, and it's purely because of the number of images that it's seen. The bias in the training data, the proportions of white faces in the data are much higher, and so the model's more accurate or less accurate at classifying black and ethnic minority. A really serious thing that happened in the US a couple of years ago was a number of states have tried to implement a machine learning model to generate a risk of reoffending score for criminals approaching their parole. And using a statistical analysis after the fact, they worked out that this model was really heavily biased against African Americans. And clearly that's they're only discovering that after it's having a huge impact on the people that are subject to those decisions. So we really need a way to fix this problem, to surface all of these issues around transparency. We certainly can't take it for granted, and unless we can see the bias that's inherent in the data sets that we use, then we don't have any way to actively correct for it. And then the really tangible thing that's come up in the last several years is the GDPR. I don't know how many people in this room have had experience getting their systems ready and compliant for GDPR. Maybe less so in the construction industry, I don't know. I think most people who have been involved in that have spent the vast majority of their efforts on the governance, the data governance side of things, so security, privacy, provenance, data access and data, the ability to delete data, the right to be forgotten and so on. But in the GDPR there's also articles that relate to automated decision making and profiling. And without going into lots of detail about that, what it boils down to is that people have a right to an explanation for any decision that has a significant effect on them. Now, a significant effect might be financial, legal, there's lots of different aspects to it, and the GDPR is actually very broad in its discussion of these issues. And for companies that want to implement machine learning automated decisions, they need to make sure that a real person is going to be the final arbiter of these types of decisions that are made about customers or people who are using their services. Obviously, this right to an explanation isn't anything new. It dates back as far as 1970 in the Fair Credit Reporting Act in the USA, but I think that's from a time before people were envisaging that machine learning was going to have such a big impact on high-skilled professions, all the knowledge-based areas. And I think that from some of the examples on the screen, you can see it now with the GDPR and the breadth of it. It doesn't just affect financial services, but really all of the areas where the individual might interact with the institutions of society are potentially involved. So my thoughts on this are that government and public sector are some of the areas that are going to be potentially very seriously affected. Now, there aren't any test cases relating to any of this because GDPR is quite new. It's only been around since May last year, enacted into law. But the regulator has demonstrated an appetite for applying penalties in cases relating to other aspects of the regulation. So I think it's only a matter of time. So, just tying it back to where we started, this black box problem poses a barrier to adoption of state-of-the-art methods. And we've seen that in financial services organisations that are sticking to using things like logistic regression because that's so well understood. There's a century of statistical theory behind it, and they're not necessarily able to get the benefits of some of the much more accurate machine learning methods that we use. So I'll move on to the good news aspect, which is that people have seen these problems coming. People who work in machine learning research are aware of it, or have been aware of this, and have certainly preempted it. The term explainable artificial intelligence is probably the kind of the de facto term to describe this area of research, and first appeared on Google Trends around late 2016. Before that, it was more generic terms like black box and interpretability would be the way that you'd recognize the research. So this is something that I produced from hits on Google Scholar, which is an academic search engine. And you can see this is the proportion of all of the hits for machine learning that also have one of these second search terms. And you can see from quite a low base in the late noughties, we've got exponential growth. So it's a very active research area. And I think the watershed moment came when the Defence Advanced Research Projects Agency made a well-publicised call for funding applications. So that's the largest strategic government body in the US saying we've got lots of money to spend on teams and projects working on this specific problem. So I'll move on to just talk a bit about how will we do explainable AI. The first thing to say is, well, let's not think about that our models as existing in a vacuum or just on a lab on some researcher's computer. In order to be useful, it's got to be deployed into an integrated system of processes. And somewhere downstream of the model, there's going to be a real person as the consumer or end user of the decision or prediction that comes out of that model. And they've got a job to do or a task that they need to complete. And they're hampered from doing so. They're blocked from doing that because they don't have access to the chain of reasoning that led to the decision they've got in front of them. Before the days of automation, there'd have been someone they could ask, but now that avenue is close to them. So one thing that we can do is just try to make more interpretable models. Make models that aren't a black box as such. And that's a perfectly valid area of research. There's a few examples here, and if anyone wants to follow these up, the references are at the end of the slides. Most of these models take the shape of a cascading rule list. So rather than a decision tree, it's like a rule list. And you work your way down the list and find the rule that matches your particular data item. These approaches just generally differ in the way that the models are trained and the rules are derived, and the types of rules they can generate. But that's the kind of general approach that's taken. Ultimately, these types of models still suffer from that accuracy interpretability trade-off. They're trying to summarize something that a more complex model will capture more completely, but they make a slightly better win-win out of that trade-off. The really active area of research, which is what I'm involved in, is in developing explanations. So an explanation will be a real-time unit, a unit of information generated in real time that supplements the decision or prediction that's given. And that information gives the end user enough knowledge that they can reason and interpret about the decision that they have in front of them, and that allows them to then complete the task that they have. I've put some of the names of these different methods or algorithms up on the screen, and they separate, I think, quite well into these two dimensions. We've got model agnostic methods on the left, which are supposed to work with any type of model, any black box model, and on the right, model specific methods that are tightly coupled to one particular family or type of model. So we've got tree shap and tree interpreter and chirps that all work with decision forests, and these other ones work with neural networks. At the top, we've got additive feature attribution methods, and I'll talk about that on the next slide. And at the bottom, classification rule-based methods. And you'll have noticed that the more interpretable models were rule lists. So clearly, rules are very useful in explanations. So the natural language of logic and reason. So that it makes sense to build explanations from rules. So additive feature attribution methods. The way they work is to take the instance that you're trying to explain. So in this case, we've got an individual who we need to classify as having as being in the lower or the upper income bracket. And additive feature attribution method will take all of the most important features that contributed something to that decision being made and generate a numeric value to associate with that feature. And then the kind of the summary or the aggregation of those values will add up to the decision that's made. So in this case, it's adding up to the probability that it will be less than or more than $50,000 US, and there are 4 of these values contributing more towards the less than 50K, and there's 1 competing value contributing more. And when they all add up, it comes to a balance point where this individual happens to be classified as less than 50K. The top graphic is from a paper on SHAP or Shapley additive explanations, and the graphic in the middle is, the graphic at the bottom is from a system called LIME, L-I-M-E. Both of these methods are very popular right now as in explainable AI research, and also more so commercially as well. A classification rule-based method, explanation implies decision. That's the rule that we want to come up with. So this is the output from the algorithm that I'm working on, and what we do here is start with the final outcome that was made, and then try to find a rule that is true of these are conditions that are true of the instance that we need to explain, but they also capture or cover as much as possible of the historical data as accurately as possible. So in this case, we found a rule which covers 40% of the historical data, and of those 40% matches over 97% is true for 97%. So it's a very good quality rule, and it's very easy. We can take this rule and use it again. We can apply this rule to another, to any other instance that matches with a very good likelihood that we're going to have a correct explanation. That's the advantage of using classification rules. I'd say with the additive feature attribution methods, they lend themselves much more to these intuitive visual visualizations, whereas classification rules are better because we can apply them across lots of different instances. In terms of whether we would go model agnostic or model specific, model agnostic sounds really useful because it works with any method. It works with any model, and it achieves that by generating a synthetic sample around the instance that you want to explain. So we take the instance we're trying to explain and then generate lots and lots of other instances that are very similar but all slightly different based on a bit of randomization. Then you pass that synthetic sample into the model, and you can do a statistical analysis of the outputs and work out which of the inputs were most sensitive to being changed that resulted in a different output. So that's pretty clever stuff, and it works really well for text and image data because generating these synthetic distributions is really a question of turning pixels on and off or swapping words in and out of a piece of text. The whole assumptions are kind of violated for tabular data because you have to look at the training data to build your synthetic sample, because you need to understand the domain and the distribution of every column in your table. So once you start looking at the training data, you're kind of outside the remit of a model agnostic method anyway. And I kind of would argue that the scenarios where you really need to be using a model agnostic method is maybe quite rare. I can only think of a third-party audit where you're trying to check the quality of somebody else's model. But it might be in those cases that if you don't have permission, then you can't send enough samples into their API to do your statistical analysis. So I think the scenarios maybe are limited in that case. What we find when we use a model-specific method is the results are more stable, the computation is more efficient, and because you're querying directly the internals of the model that you've built, you tend to get more useful and reliable results. So that's really the pros and cons of those two options. I would probably say if you're the data owner and the model owner, and there's a model-specific method that matches your model, then there's every reason to use it and not go model agnostic. The last thing I wanted to say was, if you are someone who's responsible for AI transformation or digital transformation in your organization, and you want to have a way to measure the benefits of implementing explainable artificial intelligence in your project, it's obviously very difficult to measure something like the quality of an explanation or the interpretability of a model, because these are quite qualitative concepts. They're very difficult to pin down and formalize. But the common sense approach is just to focus on the improvement in task performance downstream. And while that's an indirect measure of the quality of what you're actually doing in terms of machine learning, it's probably a direct measure of the thing that you're trying to improve in the first place. So that's me. I'll just wrap up by saying, we're just reminding where we started. There's really a trust deficit around AI generally, and in particular, very concretely, the GDPR poses some real risks to organisations who want to implement machine learning and automated decision making. But the good news is there are novel solutions out there. People are working on it very actively, and we're seeing some of this work translate into the commercial sector. Some of the things I've talked about, TreeSharp, has been incorporated into libraries like XGBoost for R and Python, and I've also seen it incorporated into RapidMiner, which is a commercial data mining software. So if you use RapidMiner and you're fully licensed, you should have access to an eXplainable AI module within that now. Okay, so that's me done. I'll hand back over to Hassan.